So hey guys, I hope you're having a great time in Singapore. I love Singapore personally. Are there any people from Israel, by the way? Can you raise your hand? Okay, I guess not. So first of all, let me introduce myself. My name is Eytan. I come from Israel. At the moment, I live in Taipei. I'm a full-stack JavaScript engineer. I do that full-time, and I also do that for fun. This is why I give a talk right now. And when it comes to programming, I really like to dive deeply into stuff which are trivial, so trivial that it's part of our daily routine and we just overlook it. And because it's something so trivial, then I'm going to dive deeply into it, and naturally it's going to be a low-level talk. So it's not going to turn you necessarily into better React or Angular developers, but at the end of the day, you'll be able to solve problems that a lot of programmers don't know how to solve, and just a new world of possibilities will open up to you. And the subject of the day is AOT compilers, ahead of time. So I assume that you're pretty much familiar with the concept, okay? Example compilers, compilers for C or C++, where you basically take a code string and you get it from one format into native machine code, or in the case of JavaScript, where you take ESNext and you compile it to ES5. Now, why is it such a trivial topic? To prove my point, I have a few questions. If it's true for you, please raise your hand. Who here uses Babel to compile JavaScript applications? Please raise your hand. Okay, a lot of people. Who here uses TypeScript? Raise your hand. Okay, again, a lot of people. Now, listen carefully. This is slightly different. Who here uses ES5 to write JavaScript applications? Please raise your hand. Get out. Get out. No. Okay. So we see that there's a common pattern here, right? We all use Babel and TypeScript and all these sort of compilers, but no one ever stopped and wondered, how does it actually work? And there's a lot of advantages to that, because once you know how it actually works, then you would know how to run some processing before you actually go to the interpreter, rather than wasting some runtime processing power. So I'm going to go through very trivial stuff, and later on I'm going to dive deeply into that, so just bear with me. Yeah, so why exactly do we use ahead-of-time compilers? What are the advantages? First of all, you can use it to optimize code. So let's say that we have parts of code that we don't actually use, such as tree shaking, where we import modules and we end up not using these modules. Therefore, we can reduce that part of code and reduce bundle size. Or for example, if we have variable assignments of variables that we don't actually use, then we can just delete that when we compile the code and therefore save some memory allocations. And why not take it a step further using linters? So basically what the linter does, it says, hey man, listen, there's something wrong here, okay? You import that module and you don't use it. Or maybe there's a standard of code that we want to just live up to our own expectations. So let's say we want to use conditions in a specific way, maybe closures in specific places, maybe we want to force use const variables. So before we actually run the optimization itself, we can basically make the code look a lot better before we push it into our Git host. Also, it enables backward compatibility. Now, we all use the latest features of JavaScript. And if I'll just open Chrome DevTools right now and I'll try to use syntax such as arrow functions, async await, and so on, it will work. But we all know that, unfortunately, there are Internet Explorer 11 out there. Okay, users that use this old browser. And we need to enable backward compatibility because we don't know what type of browser, what version of the browser the user is going to run. Therefore, we need to ensure that we use the least amount of features possible when it comes to ECMAScript. Also, when someone suggests a new feature for the set of specifications for ECMAScript, it takes time before it actually gets accepted into the language because the committee needs to look at it. Afterwards, the community needs to also see how it fits within the ecosystem. It needs to go through stages 0, 1, 2, 3, and then all the browsers, they need to implement that natively within C++, and they all need to be aligned with one another. This process takes time. Using an external compiler, this is relatively easy to just plug in another feature, and then basically there's a layer on top which is common for all browsers. So it's very easy, especially in the case of Babel, where the compiler is written in a high-level language such as JavaScript, and we also have the opportunity to test the new feature and see if it actually fits. One final reason is that we can use custom syntax, also known as language extensions, such as TypeScript, where we basically have type safety, okay, and we can see if the code actually behaves the way we want. Or we can use JSX, which is used vastly to write React applications in a better way. So obviously, there are advantages to the compilers. Wait, okay. There aren't going to be many slides. There's going to be this slide and another one, and that's it. It's mostly going to be demonstration. I hope I can get it right because I'm not used to this setup. Like they said, this is like, I'm used to Linux, and this is like another world for me. Anyways, what are the stages of the compilation? Everything that I'm going to mention, it is true for all AOT compilers, I believe, although I want to be more specific to Babel because it's very popular within the ecosystem. It's also very easy to write plugins into Babel. But yeah, everything is true for all AOT compilers out there. So first stage, first of all, we take as an input a code string, and then we parse it. Parsing, what it means is that we put it into a JSON. Okay, this JSON is basically a tree, and the tree is made out of nodes. Each and every node in that tree represent a different feature within the syntax. This tree is called AST, abstract syntax tree, because it represents the syntax. Now comes the second stage. Once we have the AST, we take it as an input, and we generate code out of it in a different format. Okay, it's very easy to do so. We basically take a specific node, and then we generate the matching code string to that specific node. In the case of Babel, it's slightly different, because Babel it's not exactly a compiler, but it works exactly the same way. It's more like a transformer. So even though you take an AST, the generated code should be exactly the same. Now, I put a lot of information out there and stuff like that. The best way to explain something is by demonstrating. So this is exactly what I'm going to do now. So let's focus on the AST first. How does the AST looks like exactly? So there's a website out there. It's called AST Explorer. This one. And let's do it. Okay. And we have two windows in here, okay? In the left window, what we have is a text editor where we can type code. In the right, we have an object, a JavaScript object, as I said, the AST that represents the code. So what happens if I type just a very generic code, nothing special about it? So we see on the right that the view got updated. Okay, and on the right, this is the AST that represents the code. Now, what's nice about this tool is that not only it shows us the AST, but it's very easy to highlight the code and match it with a correlated node. So let's highlight something on the left. Okay, wait, it doesn't use the right parser. Okay, I'll soon explain what it is. So once I highlight something on the left, it will also be highlighted on the right, and vice versa. If I hover over a specific node type, it will be highlighted on the left. So it's very easy to see what represents the code. And if we'll take a specific node as an example, let's highlight number 1 over there. And we'll look at the node, we'll see that the type name actually matches the description. Okay, this is called a numeric literal, because literally this is a number with the value 1. So this is basically an AST, and you see there are nodes which are nested with one another, and it all starts from the root. So this principle is true for all syntax and languages, and a tree doesn't need to look a certain way. There can be many parsers. So Babylon 7 is what Babel used to use under the hood. Now they renamed it. They made it part of Babel's monorepo, and they call it just Babel parser. But there are other parsers, such as Acorn, Esprima, which played a very important role when it comes to parsers in JavaScript. Flow and TypeScript. And not only JavaScript, there can be many languages. There can be CSS, GraphQL, HTML, handlebars, JavaScript. These principles apply to all syntax and languages. Okay. Now, how exactly does it look within a Node.js application? How exactly do I take code and parse it into an AST? So, because I'm here right now, I can just say anything and you would believe me, but I don't want that. Okay, everything that I say, I want to back it up with proofs. So for that, we will go to Babel's documentation website. Okay. Okay. And in the search bar, there's a library called Babel Parser. I hope you can see that. Yeah. And the API is fairly simple. We just import the parse function, and we provide it with a code string. And the output should be an AST. Now, it accepts all different kind of options, but there is, I don't want to go through it because I want to keep things simple, but however, there is a specific option that I would like to focus on. This is the plugins option. By default, it will parse only a limited set of features, of nodes. But there are different nodes which are not officially part of ECMAScript. Nodes which are in stage 0, 1, 2, or 3. So they won't be parsed by default, and for that we need to say to the parser explicitly that it needs to parse them. So features that you're probably familiar with, such as async iterator, big int that we just talked about, class properties, private class properties, and things that I'm quite frankly not even familiar with. And we can also tell the parser to support node types of language extensions. Okay, so like I mentioned earlier, there are some features which are not part of any specification, such as flow, JSX. So under the hood, this is how it happens. Babel officially supports it, and also TypeScript. That's interesting. This is not what TypeScript uses. TypeScript has a dedicated parser and compiler, although Babel also supports parsing TypeScript. Limited features of it, it's still nice to have. So now let's see a demonstration in a Node.js application. Yeah, so this is a very simple program. What I have here, I import the parse function, and then I provide it with a code string. And then I parse it, and the output is an AST. And what I do, I print to the console a stringified version of the AST. And the expected output should simply be an AST. Now I'll run the program. Wait, again, this is an environment I'm not really used to. Okay. So the output is an AST. This is just a JSON that describes the code. I'm not going to go through it because this is very boring, but I think we got the principle because of what we saw in AST Explorer. Now the second stage. Once we have an AST, we put it back into code. This stage is called generating. So I'll go to Babel's documentation website again, and we will look at the library called generator. So again, very simple API. We simply accept an AST as the first argument. The output should be code. And again, I would like to demonstrate that very quickly. Okay, good. So in addition to what I did earlier, now I have the generate function. And once I import it, I provide it with the generated AST, and I print it to the console. And the output should be exactly the same. And let's run the program again. You see, it's not exactly the same. It's slightly different because there are semicolons. Why there are semicolons? Because the AST doesn't contain information about the semicolons. It simply puts the code back in the way it can. And now, I want to go back to the slides. By the way, you see that the output is exactly similar to the input. Now, when we look at the traditional compiler, the input and the output should be different. Okay, when you look at C++, for example, because the output is in native machine code. But Babel is not exactly a compiler. It's like a transformer or a transpiler, and it works in a slightly different way. But soon I'll talk about it, and we'll see how from ES next it goes to ES5. So back to the slides. I would like to add another optional stage. It comes between stage 1 and stage 2. Okay, so stage 2 becomes stage 3. And why this is like, I do it like that, this is an optional stage because most compilers, a compiler doesn't necessarily need to have that stage in order to work properly. But this is a very powerful stage because using that stage, we can actually apply pre-processing to the code and run optimizations before we actually address the interpreter. And this is by far the most complex stage because this is API specific. There's a lot of things to know about the API, and we'll soon see why. So going back to the code, now let's say that I would like to transform the code. With traditional methods, using only regular expression, this would be very complicated because a code can have scopes, and maybe there's a piece of code which is wrapped with brackets or something like that, which makes the transformation irrelevant. This is why we have the AST. The AST makes it easy on us to transform the code. So let's say that I would like, through transformation, to change const C into const B. So how do I do that? What do I need to do is to address the right node with the right property and then change its value. And once we put it back into a code string, because the new code string is derived from the AST, then we should have a transformed code. So we copy that, and we go to AST Explorer. This is how I actually work when I write Babel plugins or I want to transform code. And I paste it. Okay, and then we see that it got updated on the right. Now, what I do, I highlight the code that I would like to transform, and then the corresponding node is being highlighted on the right. Now, what I do, I need to look for the path that represents the node. So I start from the root, and I write down the path. So it goes to program, body, position 0, declaration, position 0, ID, name. Let's say that I wrote everything down in the text editor, and I have it right here. Yes. Yeah. So I changed the AST, I changed the value C to B, and therefore once I put it back into code, the expected output should be the following. You see? So I changed the code. Now, there's a problem with that approach. Because what I did right now is too specific. I want to have like some sort of a generic pattern that I can apply, and it will be true for any code string that I get as an input. Something like regular expression, okay? Because a code can wear many shapes and forms. This is way too specific. So there's a problem with that approach. Many compilers, they implement a mechanism and they provide us with an API which lets us transform the code in a more generic way. Okay? So using that API, what we do, we basically walk through the AST, through each and every node in the AST. You can call it walk or run or traverse. Essentially, these verbs, they all represent the same thing. And then we apply transformation callbacks for each and every node individually. So if we'll look at the AST, and we'll try to demonstrate it, what it does, it starts with the root, it goes through the root node, it goes deeper to program, variable declaration, and then once it sees a transformation callback, then it goes to the callback, applies the logic, and then it keeps walking through the tree. If we look at Babel's documentation website, there's a library called Babel Traverse. And traverse does exactly what I said. As the first argument, it accepts an AST. As the second argument, it accepts an object, which is called a visitor, because this object visits the AST as we walk through it. And this object contains callbacks. The names of the callbacks represents the nodes that it is going to transform. And as the first argument, it accepts an object that contains the node. And then we can actually do all our changes on the node that we would like to transform, and we can also apply conditions and logic to it. It also accepts more arguments. I don't want to get into that because I want to keep things very simple. Once you understand the core, it's very easy to get deeper and investigate more about the subject. So let me show you another demonstration of that. So in addition to what I had earlier, now I use the traverse function to traverse through the AST, and I apply transformation callbacks. So if I have that input, what I would like to have, the expected output should be something like that. So let's say that I change all the variable assignments from whatever this is to B. Everything should be B. And the values should all change to 2. And Fn should change to Fn2. So this is the expected output. So how do I do that? I use the right callback names with the right visitor. And then I change the corresponding nodes. Again, how do I know how does the API looks like and what nodes to address? I go to AST Explorer, and then I highlight the code, the parts of the code that I would actually like to transform. And then I look at the node. I see what is the name of the node, and I see how the signature of the node looks like. And this is how I know how the API looks like. Now, if I will run the code, the output should be what I just wrote over there. You see? And just to prove it to you that this is a general pattern and it's not just specific to that code, I can add another variable assignment over here. and this should change to b equals 2 as well. Right, this is nice. Now, this is how we transform code. So the visitor over here, this is what a Babel plugin is all about. A plugin is just a visitor. Okay, Babel wanted to make it easy on us, and they wanted to give us a way to implement custom features using plugins. And so in order to do that, what we need to do is simply to write a visitor. And what we do, we specify it in the Babel RC, then it looks for the right name in the Node modules, and then it applies the visitor once it walks to the AST before it actually compiles it. Now let's see an example plugin. So what I have here is a program which the input is exactly the same as we had earlier, and the plugin is exactly what we had earlier. Again, a plugin is a visitor. It accepts more options that will make it easy on us to transform the code. But again, I want to keep things very simple. Because the visitor is the same and the input is the same, therefore the output should be exactly the same as well. So I'm going to run the program again. And the output is exactly the same. Now, how exactly from that do we reach ES5? Okay, because so far it looks like it remains to be ES next. So ES5 is simply a set of plugins that transforms the code in a way that it will, from ES next, it will turn into ES5. A set of plugins is also called a preset. This is what a preset is. A preset is simply a set of plugins. So, in order to transform to ES5, what we do, we load a set of plugins using the Babel env preset. The env preset, what it does, it applies plugins based on the environment that we would like to transform to. Okay, how does it know that? Based on what's written on package.json. Now, I'm going to apply this plugin, and you'll see that it will be transformed to ES5. And let's make the input a little bit more ES next. And we'll run the demo again. And the output is ES5, as you can see. So this is how Babel works. Okay, this is how it works. Now, what's the point of it? Okay, why is it such a powerful tool? Because using that knowledge, you can write plugins yourself and enhance the user experience as a programmer. So I'll give you example plugins that I wrote myself. You don't necessarily have to agree with what they do. Maybe you don't like their functionality, but again, just understand the power behind that sort of information. Okay, so first plugin is a plugin for, if you're familiar with the new React Hooks API. Here what I do, I transform data. Okay, and the problem is that once I enter the rendering phase, each and every time I would need to apply that logic. Or here, if I have anonymous callback, each time I enter the rendering phase, I would need to initialize that callback. So what I need to do is to cache the result using use callback or use memo. So with that plugin, you can automatically apply use memo with the right arguments. You just type it normally, as you would, and then it optimizes the code for you ahead of time. Or it also does things like creating anonymous components where it caches the callback results, and you don't need to put use callback and therefore save some errors. Second and final plugin that I wrote, something for styled components. Rather than creating a dedicated component per each component that you would like to encapsulate its style, you can use a single style sheet component and use underscore to encapsulate private class names. And what the plugin will do, it will prefix it automatically, therefore encapsulate the styles. So that was basically it. I hope you liked it. There isn't much information about it online. Documentation is very, very poor. But I did write a few articles about it, and I'm also going to upload a video about it. And also, be sure to use AST Explorer and Babel docs. If you have any further questions, feel free to address me later on in the break. And thank you.